Hello, welcome to the course on Emerging Domain Electronics Engineering. This is lecture 19, and in this lecture we'll see the number system and the arithmetic operations. So in the last lecture we have seen that how we can perform the addition, subtraction of the numbers, and we have seen the representation of numbers, that is a binary, decimal, hexadecimal and octal. After that we have seen that how we can convert a one number system into the another number system. So here we can see that means we didn't see how we can represent the negative numbers till now. We have represented the positive numbers in all the four forms, mean in a binary form, decimal, octal and hexadecimal form. So now in this lecture we will see how we can represent the negative numbers, and we will see how we can perform the subtraction of two numbers. So the negative numbers have got two representations. One is a complementary representation and the another one is a sign magnitude representation. So we will see how the complementary representation will be there, means in a ones complement form, twos complement form, nines complement form and the tens complement form. So first of all we will start with the ones complement form. So ones complement of a binary number is obtained simply by replacing each 1 by 0 and 0 by 1. Alternatively, what we can say that we can subtract each digit or each bit from 1. So we have a small example over here that we need to find out the ones complement for 0 1 1 0 0 1. So how we can perform? If we'll go with this first approach, that we will first convert 1 to 0 and 0 to 1, then we can clearly see here that 0 is converted to 1. Similarly 1 is transformed to 0 here, again 0, this is 1, this is 1 and this is 0. So this number which is 1 0 0 1 1 0 is a ones complement. Ones complement of the given number. We can use the another alternative method also. So this alternative method says that we can subtract the number, the given number from 1 1 1 1, like that, means the each and every bit is subtracted from 1. So here we can say clearly that this subtraction 1 minus 1, we have the 0 here, over here, again 0, this is 0, 1 minus 0, we have 1, again we have 1, 0, 1 and 1. So this is the ones complement representation of both the numbers, means we can use both the methods to obtain the ones complement. So after this we have the twos complement. So twos complement is nothing but first we need to perform the ones complement, and after that we will be adding 1 to the LSB. Means first of all there means in the twos complement it involves two steps. First step is the ones complement, and after that addition of 1 in the LSB. So if we need to find out the twos complement of this 0 1 1 0 0 1, then first it is a ones complement which is given by 1 0 0 1 1 0, and we will be adding 1 to the LSB. This is LSB. This bit is LSB. So we'll be having 1 0 0 1 1 1. This is known as the twos complement of this given number. Again we have a second example, let's say 0 1 0 1 1 0 0. Then again how can we perform the twos complement? First we will perform the ones complement, and after that we'll be adding 1 to the LSB. So in this way we can have the twos complement of a given number. Now we'll see what is the nines complement. So nines complement and tens complement are the methods used for representation of decimal numbers basically. So they are identical to the ones and twos complement used for binary number. Means for binary what we have ones and twos. For decimal we have nines and tens. We can have any kind of complement, anything, means we can have the third complement, fourth complement also. We'll see r and r minus 1 complement also, right? So first is the 9's complement. So 9's complement of a decimal number is defined as, means how can we calculate 10 raised to power n minus 1, and this is in bracket minus the actual number n, where n is the number of digits and capital N is a given decimal number. Or the alternative method is, then we can subtract each digit from 9. Means if we have, let's say, a number which is of 4 digits, then if we are subtracting each digit from 9, then we can also have the 9's complement. So this is a generalized formula, 10 raised to power n minus 1 minus of n. So if we use this for this particular number 459, which is given in a decimal form, it contains, let's say, small n equals to 3 and capital N will be, let's say, 459, the actual number. So if we'll put over here, so that will be 10 to the power 3 minus 1 minus 459, which comes out to be 540. So 540 is a 9's complement. Or alternatively, what we can do, we can subtract each digit from 9, means 4, 5, 9, and we will subtract. 9 minus 9 is 0, 4 and 5. So means here both the answers are same. You can see 540. Now we have the 10's complement. So what is 10's complement? Again, likewise we have seen in the 1's complement and the 2's complement. Similar is the situation for the 9's and 10's also. So for 10's complement, what is a generalized formula, which is 10 raised to the power n minus the actual number. Else what we can do here is, if we can add and subtract 1, means minus 1 plus 1. So this whole thing is nothing but, if you'll remember, that it is a 9's complement of n. So this is the formula for 9's complement of n plus 1. So in a similar fashion, we have we have already seen in the 2's complement that we are adding 1 to the LSB. Similar in 10's complement also, first we will obtain the 9's complement and we will add 1 to the LSB. So if we have the example, again we have 459 and we need to convert this into the 10's complement form. So 10 raised to the power 3 minus 459, which is 541. Else what we can do over here, this is 999 minus of 459. So this is 540 again plus 1. So this is 541. This is the 10's complement. This is the 10's complement. So these are the methods to obtain the 1's, 2's, 9's and 10's complement. Now we will see how we can perform the subtraction using 1's complement form, and after that we will see the 2's complement method also. So previously what we did is, if we want to subtract two binary numbers, so directly we will be able to find out, right? But now using 1's complement, how the subtraction will take place, we will see. So the method for subtracting the two numbers of equal length. So one is a minuend, one is a subtrahend. So by introducing leading zeros, means first we need to have the length of both the numbers equal. So how we can achieve this? By inserting zeros at the beginning, at the at the MSB positions. After that we will be taking the one, means if what are the rules for 1's complement subtraction? First we'll take the 1's complement of subtrahend. Let me just tell you, if we want to perform this subtraction m minus n, then how we can subtract? So this is subtrahend and this is minuend. So first we need to take the 1's complement of subtrahend. After that we will be adding the ones complement of subtrahend to the minuend. After that, these steps are quite important, third and fourth. If the carry is produced, we will see this carry is known as end around carry. Means if the carry is generated from the MSB, then we need to add this carry to the LSB. So we'll be adding that end around carry or that generated carry to the LSB. And after that, this fourth point is very important, that if carry is generated from MSB in step 2, then result is positive. If carry is not generated or if no carry is generated, then the result is negative. And again how we can correct our result? Again we will take the ones complement. Means for that particular result, again we will take the ones complement. So that is the answer. So if we will perform the subtraction of two numbers, let's say 7 minus 3, we are aware the result is 4, but we will use the ones complement form. So first, this is the subtrahend, let's say this is capital M, this is capital N. So the first step is, first we need to take the ones complement of N, which is nothing but 1100. After that, perform addition of minuend and ones complement of subtrahend. So we will be adding this M to the ones complement of N. So 0 111 is same and 1100 is the ones complement. So we need to perform the addition over here. 1 plus 0, 1, again 1, 1 plus 1 is 0, 1 carry. So this is 0, 1. So this is known as the end around carry. EAC, end around carry. So we will be adding this end around carry to the LSB, over here. So this result will be, we'll have this 1 plus 1, 0, again 1 carry, we'll have 0 and 1. So 0, 1, 0. So now we need to go to the fourth point, what we have discussed, that if the carry is generated, so the result is positive. The result is positive. So the answer will be plus 4. Right? So we are understood that 7 minus 3 is plus 4. Now if you need to perform 3 minus 7, let's say. So 3 minus 7, if you will write down over here, 3 minus 7. So 3 is basically 0, 0, 1, 1. 7 is basically this. So again for 7 we need to take the ones complement. So that will be 1, 0, 0, 0. Now we need to perform the addition. So 1, 1, 0, 1. So can you tell me what is the end around carry? End around carry is not generated. EAC is not generated, or we can say no carry. If there is no carry, then again take the ones complement of the answer and the result is negative. So this is 0, 1, 0. And the result is negative. So minus and 0, 1, 0 is 4. So the result is minus 4. The result is minus 4. As we can see, 3 minus 7 is minus 4. So in this way we can perform the subtraction using ones complement. Now if we will see what is the method for the twos complement. So again some steps remain same. That first is, what are the rules? We will see. Take the twos complement of subtrahend. Again let me just clear this, what is subtrahend and minuend over here. This is subtrahend and this is minuend, capital M. So what we need to do is take the twos complement of subtrahend, which is N. After that add twos complement of subtrahend to the minuend, which is capital M. Now if the carry is produced, then discard it. Then we need to discard the carry and the result is positive. If no carry is produced, then the result is negative, and again we need to perform the twos complement of the result what we obtained. So these are the this is a method for twos complement. This is somewhat different from 1's complement. So if we'll see some example over here that performs 7 minus 5 using the 2's complement form. So 7 we have 0 triple 1 and 5 we have 0 1 0 1. So we need to perform the 2's complement. How can we perform? First we will be having the 1's complement of 5. So 1's complement of 5 will be 1 0 1 0. This is the 1's complement. Now if we'll add plus 1, then this is 1 0 1 1. This is the 2's complement. 2's complement. So this is the 2's complement, and this is 7 0 triple 1 and 1 0 double 1. Just perform the addition. So please see over here that 1 plus 1 is 0, 1 carry, again triple 1, it is 1 1. So 1 over here, 1 over here. 1 plus 1 0, again 1. 1 plus 1 again 0 with 1. This is EAC, end around carry. So what we have seen, if the carry is generated, then discard it. Then discard it, and the result will be positive. The result will be positive, and this 0 0 1 0 is equivalent to 2. So the answer is plus 2. We can have opposite also, which is 5 minus 7 also. So the result will be means we can use the same steps to obtain the subtraction 5 minus 7. So we'll have the negative answer, which is minus 2. After this we have the subtraction, rules for subtracting the r's and r minus 1 complement. So again let me summarize what we have seen for 1's, 2's and 9's and 10's complement. So first is that we need to equate the length. After that, represent negative operand for negative numbers only. After that, complement the subtrahend. After that, the addition and the carry. After that, the process of the carry, CY, which is end around carry. After the result manipulation. What we have seen in 1's and 9's, quite similar, and for 2 and 10's, the manipulation is quite similar. So after that, the post processing and the result declaration. These are the steps for performing the subtraction using r's and r minus 1's complement. Now we have the representation, which is called as a signed binary representation. So signed binary representation means in computer what happen is that for positive or negative number, if we want to represent a positive or negative number, so there is a bit defined for positive and negative numbers. As we can see over here, that 1 is used for negative sign and 0 is used for positive sign. 0 is used for positive sign. So in sign representation, MSB, which is the most significant bit of the given binary string, represent the sign of the number. In all type of representation, we will see what are the types of sign representation, sign binary representation. So we have two types of sign representation. One is the sign magnitude representation and one is a sign complement representation, or what we can say the sign magnitude form and signed complement form. So what is the difference over here? In sign magnitude representation, the most significant bit represent the sign and the rest of the bit representation denotes its magnitude. Means if we have plus 5, so corresponding to plus we can write 0 and 5. What is the magnitude? Means the magnitude representation for 5 is 101. So result is 0101. So automatically it must be understood that if the MSB is 0, then it is a positive number and the rest bits are the magnitude. So it is plus 5. Similarly over here what we can see, minus we have 1, and corresponding to 5 we have 101. So if we have 1101, so automatically it will be understood that if it is represented in a sign magnitude form, then it is corresponding to -5. The MSB, this is the MSB is corresponding to negative, and remaining part is corresponding to the magnitude of 5. So the range of the sign representation is from minus of 2 raised to power n minus 1 minus 1 to 2 raised to power n minus 1. This is a range. Means for n bit we can have we have this particular range. So after this signed magnitude representation, we have the signed complement representation. So in a signed complement representation, the positive numbers are represented in a true binary form with MSB equal to 0, whereas in the negative number, by taking the appropriate complement of the equivalent positive number, means for that number, positive number, will be using the complement method, what we have seen, the ones complement form and the twos complement form. So including the sign bit, so both the ones and twos complement can be used for this purpose. For example, if we have the plus 5, so plus 5 means 0 and 5 corresponding to 101. Now if we have minus, basically the sign binary representation is for the negative numbers, right? Because in representing the positive number we don't have any difficulty, we have the difficulties for the negative numbers. So minus 5, if we want to represent in this form, so negative means minus, we have means directly just take the ones complement, directly take the ones complement of the result of this particular result. And if we want twos complement, so again just perform the ones complement and we will add 1 to the LSB. So in this way we have both, means the ones complement representation and the twos complement representation of minus 5, a negative number. And here we can say that if we have means n minus 1 bits are used for magnitude, the range of the numbers will be, for ones complement we have 0 to 2 raised to power n minus 1 positive number. For negative we have minus 0 to minus of 2 raised to power n minus 1 which is for negative number. Similarly again we have the range for twos complement also. So we have seen that what are the ranges of the ones complement, twos complement and the signed magnitude form. After that we have the codes. Again this code basically takes, means it is having a very important role in digital electronics. So coding and encoding, or we can say the encoding, is the process of assigning a group of the binary bits, commonly referred as the bits. So to represent or identity or relate to a valued items of information. So by assigning each item of information a unique combination of ones and zeros, means by assigning a combination of zeros and by assigning a combination of ones and zeros, we transform some given information into another form. In short, a code is a symbolic representation of an information transform. The bit combinations are used, are referred as a code words. So there are many different type of coding schemes available, each having some particular advantage and characteristics. So one of the main effort in coding is to standardize a set of universal codes that can be used for encoding purpose. So generally we have some standard codes. So first is the weighted binary code, non-weighted codes, error detecting code, error correcting codes, alphanumeric codes. In communication, in digital communication, we will see the error correcting and the detection and this error detecting codes. we have the Hamming codes, we have the cyclic codes. So, but here in digital electronics, we'll be seeing this weighted and the non-weighted codes only. So, the weighted binary codes, in these codes, each position of a number represents a specific weight. So, we have talked about this weight somewhere in the number systems when we are going with the binary, octal, hexadecimal and decimal representation. So, the bits are multiplied by the weight indicated, and the sum of these weight bits give the equivalent decimal digit. Means if we will have 0, 0, 0, 0, then here the weight is 8421, and if all the bits are 0, then the decimal representation will be 0. If we have, let's say, 0001, then 1 multiplied by 1, we have 1 over here. After that, 0010, so corresponding to this tens place, for this particular location, 2 multiplied by 1, the result is 2. Let's see for this 0011. So what is the decimal representation? 2 plus 1, 2 multiplied by 1 plus 1 multiplied by 1, which is 3. Similarly, we can see for 4, 5, 6, 7, 8, 9. So since it is decimal, so we are going from 0 to 9. 0 to 9. So this is the 8421 codes, weighted code. We will see what is this 2421 and axis 3. These are not the weighted code. We will see. So now we have the non-weighted codes. So these codes are not positionally weighted, means corresponding to that particular location or to the particular place, the weight is not defined, we can say, means the weight, the result, the decimal representation is not as per the weight. So this means that each position within a binary number is not assigned a fixed value. So some of these non-weighted codes are axis 3 code and gray code. So axis 3 code means if we have 643 at base 10 and we want to basically convert into axis 3, how we can perform? We need to add 3 to each digit. So 3, we have 3 over here, 3 over here and 3 over here. So 3 plus 3 is 6, 7 and 9. So 976 is the axis 3 representation of 643, which is given in the decimal form. After that, we have the gray codes. So we'll be having that how we can convert a binary number into a gray codes. So placing a leading 0 before the most significant bit in the binary number. This is the first step. After that, the XOR adjacent bits together starting from the left, means from the left side will move. So after that, what is the XOR for this? Means directly what we can say, we have 0 and this XOR, 0 XOR with 1, we have 1, again 1 XOR with 0, we have 1, again we have 1, again we have 1, 0, again we have 1, we have 1. So this is the answer, means 4 times 1, 0 double 1. This is a gray code representation of the binary. After that, we have the gray 2 binary. So gray 2 binary, again what we can do is we'll just write down the number over here and we can perform the XOR with this. 1 XOR with 1, we have 1 XOR with this particular one, the result is 0. Similarly like this, 1 XOR with 0, we have 1. So in this way, if we'll perform the XOR operation, we will achieve this particular result. This is the gray 2 binary representation. These are the references. Thank you.